Okay, so we'll continue talking about the CPU structure, and as you already know, the CPU must do the following operations, which are fetch the instructions, interpret the instructions, which is the decoding part, fetch the data or the operands, and finally it needs to um, process the data and find and write the result into some sort of memory or register. So registers must have CPU must have some working space. You need some place as a scratchbook or a place to write your results in. So usually we use the registers. So the registers have different they have different numbers. They vary in numbers and functionality. زي ما حكينا, as we said earlier, we have general purpose registers and special purpose registers. Now, one of the major design decisions is the number of the registers inside the CPU, because this will either complicate or make things easy inside the CPU. The problem of having a lot of registers they consume a lot of power, and registers they take a lot of the CPU space. So it's basically a little bit different or not that straightforward to say, okay, I will have 1,000 registers and make my life easy, but you can have only a few dozens of registers inside the CPU. Now the registers are general purpose, data, address, and conditional codes. These are the user visible registers. Yani, as for me as a register, I can see the general purpose registers, the data registers, the address registers, and the conditional code registers. The general purpose registers may be true. General purpose may be restricted and may be used for data addressing, such as the segment registers. For data, usually we have the accumulator for the AX, the BX, the CX, and the DX. And for addressing, we have the segment registers, we have the source index and destination index registers. Now, the general purpose registers, we make them general purpose. They increase the flexibility and the programmer option. They increase the instruction size and complexity. Now, remember, as I said earlier, you cannot have a lot of registers inside the CPU. There is always a limit for the number of registers that can be put inside the CPU. This limit is controlled by the amount of power that can be given to a CPU and the size of the CPU. So we make them specialized, smaller, faster instructions, but they come less flexible. So it's always a trade-off when it comes to a CPU. The number of general purpose registers is basically between 8 and 32 registers. Depends again on the complexity of the CPU. Fewer means more memory access, but more does not reduce the memory references. We are going to see the reduced instruction set, inshallah, in the next semester. But if you have fewer registers, this means that all the information you are going to get is from the memory. If you have more registers, you are going to, up to a certain point, have faster programs, and then it will you will not have faster programs, because you are going to face the problem of addressing these registers. Now, how big is enough in terms of registers? Large enough to hold the full address. Yani, if I'm working with a 32-bit address, I want my register to handle 32 bits. If I'm working with 16, I want it to handle with 16. If I'm working with 64 bits, I want my registers to handle 64 bits. So I want the registers to hold that. As you saw in the normal registers, which is AX is a cascade of two registers, which AL and AH. Cascading the registers and splitting the registers make things very interesting and very easy to deal with, because sometimes you want more data, but you don't want to change the full structure of your CPU. So instead, all you have to do is to combine registers together. So how big we want the registers to hold a full word, often possible to combine two data registers together. The conditional registers, it's a set of individual bits such as the flag register, which we talked about earlier, can be read implicitly by the programs such as in jump if 0 or loop if non-zero, and cannot usually be set by the program. It's very difficult to set the registers. The only bit that we can set is the carry bit. There is a function that will set the carry bit, which is STC, which is set carry. The flag register, very difficult to manipulate. Usually you don't have access to all the bits for that flag register, and you cannot change all the bits inside the flag register. However, some bits can be manipulated. Now, the program counter points to the next instruction to be executed. This one you have to remember it. The instruction decoder holds the current instruction which is being executed. The memory address register holds the address for read or write. The memory buffer register holds the data to which is read from the memory, or the data which is going to be written to the memory. So each register has its own function. You need to understand that the program counter always points to the next instruction to be executed. The program counter always points to the next instruction to be executed. So the program status word, it's the conditional code, a set of bits, which is the conditional codes, the sign of the last result, the 0, the carry, the overflow, or what we call it, the flag register. Flag register is basically holds the status of the CPU. What is the conditional codes? What is the sign of the last result? What is the Z? What is the? Is it a 0? Is it a carry? Is there a carry? Is there an overflow? Which is very important. So this is an example of a computer organization, which is the microprocessor 86000. You can see here we have the general purpose registers, which are AX, extended AX, BX, extended BX, CX, extended CX, DX, extended DX. Then you have the stack pointer, base pointer, source index, destination index, and their extended versions. As you recall, this is 16 and this is 16, which makes the extended versions 32 bits. We have the flag register and the instruction pointer. This is for the Pentium 2, which is the 386, which is 32 bits. The 8086, which is 16 bits. As you can see here, we have the AX, BX, CX, DX, source, stack pointers, base pointer, source index, destination index, code segment, data segment, stack segment, and extra segment, instruction pointer, and flag register. All of these are all 16 bits. When you go for the Pentium, you end up with 32 bits, and you will have the extended versions of these registers. This is the microcontroller or microprocessor 68000. As you can see here, we have the data registers, we have the address registers, you have a program counter. This is not very commonly used, but what we are concentrating basically in our studies is these two microprocessors, which is the 16-bit and the 32-bit. The 8-bit we have studied in the microcontroller part. We have something called the indirect cycle, which may require the access to fetch operands, and indirect addressing required more memory accessing and can be taught as additional instruction subcycle. This is for indirect addressing. When you have an address which is indirect, so you need to access the memory, but you need a method to find out how to access that memory. So this is handled using the indirect cycle. So fetch, execute, interrupt. If you have a fetch and you have an indirect, then you go fetch, indirect, then execute. Now this is the diagram with indirect cycle. You see here we start with fetch, then we do the decoding, we fetch the operands. In fetching the operands, is there an indirect operation inside fetching the operands? Once we finish, we go for data operation such as addition, subtraction, whatever. Then we calculate where we are going to store the result. We store the result, and we maybe have some indirect result storing. Once we finish, we check for interrupts. If we don't have interrupts, we go back. If we have interrupts, we service the interrupts, and then we go back to our next instruction. This is the state diagram with indirect addressing. So the flow, this depends on the CPU design. In general, we go for fetch, which the PC contains the address of the next instruction. We have the memory address register is moved to the address. The address is placed on the address bus. The control unit requires the memory to read. The result is placed on the data bus and copied to the memory buffer register, then to the instruction register. And meanwhile, the PC is incremented by 1, which we have already discussed. The instruction register is examined. If indirect addressing is required, the indirect cycle is performed. The rightmost n bits of the memory buffer register is transferred to the memory address register. The control unit requires memory to be read, and the result or the address of operand is moved to the memory buffer register. This is just how to fetch the indirect addressing method. Again, this is the same idea all over again. You have your PC. The program counter will put the address in the memory address register. It's put on the address bus. The control unit sends to the memory an instruction to put the data on the data bus. Then the data is read through the data bus to the memory buffer register, then put into the instruction register. This is the fetch diagram. The fetch diagram with indirect, you are going to take the data from the memory buffer register, put it again in the memory address register, fetch the data, and then you are going to read your result at the end. Now, the data flow execute may take many forms depending on the instruction being executed, and may include memory read, write, input, output, and data transfers. And again, you may have some interrupts. Nothing here. Okay, so this is just only mostly theory, but what I wanted to discuss is I want to go to the next part, which is week number 10. Now, okay. Let's talk about actual programming. Now, first thing we are going to discuss is the Little Endian convention. Little Endian from end, okay? So the least significant bit is at the right. Now, if I'm going to save data, okay? If I'm going to save data, we have byte 0, byte 1, byte 2, byte 3, and so on. This is the addresses, and this is your memory. The least significant byte at the lowest address. The least significant byte is stored at the lowest address. يعني إيش؟ يعني if I have memory, okay, and this memory will have the addresses, address 1, address 2, address 3, address 4, and address 5, and I tell you move A347 to memory location 1. So the least significant byte is saved at the lowest address. معناته this is 2 bytes. This is a number of containing 2 bytes. This byte, which is the least significant byte, will be stored at the lowest address. Which is the lowest address, 1 or 2? 1. So 47, then A3. So in the memory, you are going to find 47, then A3. يعني the opposite. What you think of that it will be stored A3 47. No, it is stored 47, then A3. The data types, we have the byte, which is 8 bits. We have the word, which is 16 bits. We have double word, which is 32 bits. We have quad word, which is 64 bits. Now, Pentium 3 processor introduces a new type of data, which is 128 packed data. We are not going to use the 128 packed data, so we are going to focus basically on the byte, word, double word, and quad words. Now, words, double words, and quad words are natural boundaries of words. For words, double words, and quad words are even number addresses. Addresses evenly divisible by 4 and addresses evenly divisible by 8 respectively. So your addresses in words are and double words and quad words are either even numbered or numbered evenly divisible by 4 or numbers evenly divided by 8. ايش يعني؟ يعني ال addresses, if you are using word, and remember our memory can hold 1 byte at a time. So if I'm using this is, let's say 0, 1, 2, 3, 4, 5, 6, 7. If I'm using word, then my addresses will be evenly 0. My address will start at 0, then will start at 2, then will start at 4, then will start at 6. So my addresses are even numbered addresses. Even numbered addresses. If I'm using double word, then my addresses are divisible by 4. Okay, so if I start with 1, then I will have if I start with 0, then I will have 4, then I will have 8. If I'm using double word, then I will have 0 and 8 immediately. This is the idea. So words, double words, and quad words do not need to be aligned in memory on natural boundaries. Data structures, especially stacks, should be aligned on natural boundaries. However, in normal data, we don't have to be like this. Yani it's not a must to have 0, 1, 2, 3. No, your data can be stored 2 and 3, can be stored 3 and 4, can be starting the addresses at 4 and 8, and so on. So, for example, over here, if I have the address at BH, okay, if I want the address at BH and I want to read a word means word 2 bytes. So BH means BH and CH. BH and CH. Remember, we always go up. So BH and CH. So I'm going to read these 2 bytes. These 2 bytes, remember, the lowest byte is stored at the lowest address. So it is 06FE. 06FE. You write it like this. So you end up with FE06. The lowest byte is stored in the lowest address. The lowest byte is always stored in the lowest address. Another instance, if I want to read a quad word, the quad word, how many bytes? The quad word is 8 bytes. Okay, هذا الكواد. Quad word is 8 bytes. I want to read a quad word starting at address 6 hexa. معناته, this means I will start from 6 hexa up to D hexa, and my lowest byte will be in the lowest address. So 0B, 23, A4, 1F, 36, 06 FE 7A. This is my information which is stored in a quad word. If it's a double word, then I will go 36 and start an AH, 06 FEAH, which is this number. The same applies over here. This is called the Little Indian method for reading the data. Again, once more, this means that the lower byte is always stored in the lower address. The lower byte is always stored in the lower address. Now the data types, we can have the binary coded decimal integers, which are unsigned for integers with value from 0 to 9. If you recall the BCD, it is similar to the hexadecimal numbers, and the BCD on the other hand will count from 0 to 9. Converging from any value to BCD is quite simple, and BCD mostly is used in the 7-segment displays. We have unpacked BCD. Unpacked means one BCD digit per byte. يعني ال 8 bits. I think there's here. This is the BCD. Okay. The unpacked BCD, in 1 byte you are going to store the first half is a BCD number and the second half is a don't care. في الpacked BCD you are going to use 2 BCD numbers in 1 byte. The same applies for a BCD inside a word or a BCD inside a packed word over here. So if it's unpacked or packed, 2 BCD digits per byte. In packed, لما يكون packed, this means 1 BCD digit per byte. For packed, it is 2 BCD digits per byte. The value of the unpacked BCD integer is the binary value of the lower half. The higher half from 4 to 7 can be any value during the addition or subtraction. The packed BCD integers allowed to have 2 BCD numbers inside the byte, as you can see over here. Now, in Pentium registers, remember we have the 80, 86 and the x86 values. The 80, 86 هدول كلهم 16 bits. These are 32 bits, or what we call them the Pentium processors. The Pentium processors are similar to the normal processors, however, they have the E letter in the beginning. E stands for extended. The E stands for extended. Each has a special use as well. EBX is used for holding pointers. CX is very good for the looping. DX is very good for multiplication, or is used for multiplication and division, as we are going to see later on. AX is used to hold data of 64 bits for products and division. EDX is used to hold 64 bits with EAX in multiplication and division. راح أجيهم. We will talk about all of this as we go through the arithmetic operations. The same, we have extended source index, extended destination index, extended base pointer, extended stack pointer. Are more or less general purpose registers, but they are more complicated special uses. So source index is used to source data, destination index used for destination pointer, base pointer is used in the stack, and the stack pointer points to the top of the stack at all times. بعدين عندنا segments. We have code segment, data segments, stack segment, extra segment, F segment, and G segments. The segment registers hold 16 segment sectors, a special pointer that identify the segments in the memory, and finally we have the extended flags, as we talked about earlier. I'm going through all of this fast because it's just revision to what we started, because we are going to talk about mostly about programming in assembly language. next week and in module 4. So that's around 1 month, which is needed to understand how to program assembly. طبعا الفلاج register, if it's a 32-bit flag register, you will have this configuration. You have the carry parity auxiliary 0, sign T is for trap, interrupt, direction, overflow, input output, nested, resume, virtual, align, virtual, and ID flag. Some of them we will use, most of them we will not use. We will use the carry, we'll use the 0, we will use the overflow. These 3 we are going to use them. No need to worry much about them. As we go through, we are going to discuss them one at a time. We have the extended instruction pointer, which is holds the next instruction to be executed للمرة المليون. They changed during the fetch boundary. Extended instruction pointer cannot be accessed directly. الطريقة الوحيدة انك تغيره, to change it, you need to use the jump, the call, and the return, and the loop instructions. Now, operand addressing can be located in any of the following places: the instruction itself, a register, a memory location, or an input-output port, depends on the addressing mode. Now, the operand addressing, an Intel instruction machine acts on 0 or more operands. So we have instructions with 2 operands. We have instructions with 3 operands. We have instructions with 1 operand. So usually we have the operation, destination, and source, such as move AX, BX, which is a 2 operand, and we can have a single operand, which such as move, such as mul BX. So this is an instruction with a single operand. Now, the move instruction. Move performs basic load data and store operations between the CPU and the registers. Move can transfer data between registers. Move can transfer data between memory location and register. Move cannot transfer data from one segment to a register to another segment register. So just this one needs to be fixed. Type. I can do move AX3. I can do move AX BX. I can do move AX BX. I can do, and the other way around. I cannot do, I think there is here, right? Okay. I cannot do move code segment stack segment. So cannot move data from one memory location to another. Also, this one is not valid. We cannot do move AX BX but with memory. Memory, you can only have one memory access per instruction. You can have one memory access per instruction. You cannot have 2 memory accesses per more than one instruction. So move can transfer data between registers. Move can transfer data between register and memory. Move cannot access memory 2 times. Move cannot transfer from one segment register to another. Data encoded in the instruction itself is called immediate operands. Immediate operands such as move CX5. ال5 اسمها immediate رقم. Such as also here add EAX14. An immediate operand can only be a source. You cannot say move 15AX. This value cannot be a destination. An immediate operand cannot be a destination, can only be a source. وللتذكير, you always have your source on the right, then you have your destination on the left. Your source on the right, then you have your destination on the left. An arithmetic instruction, except div and idiv, allow immediate operands. The maximum value allowed for an immediate operand um, varies among instructions but never greater than the maximum allowed for a double word integer اللي هو 2 للقوة 32 2 to the power 32. So you can have, this is right, this is wrong because you cannot have the 15 as your destination. This is right and this is right and this is right. These are all valid instructions. Okay, I will stop over here and we will continue on this inshallah next Monday. Do you have any questions on this part?